Alright, so let's solve this problem of shear force bending moment diagram for a simply supported beam. A simply supported beam is a beam just like this that is supported at these ends here, right? As opposed to a cantilever beam. A cantilever beam is something like that, and it is fixed at one end and the other end is left free. However, a simply supported beam, it has supports, typically two supports. Okay. So in this case, let's solve the problem for the simply supported beam. All right, so in this case we have these two supports at A and B, and then there is a uniformly distributed load that spans 18 newtons per meter. So for every meter it is 18 newtons. Now it spans over a range of 4 meters, so 18 times 4 is 72 newtons. So this entire load is 72 newton, which has been spread over a length of 4 meters. But for now we'll just ignore this for now and move on. Okay, first thing we need to do is find this reaction. How much is these reactions? I'm going to call this RA, RB. R for reaction, A subscript A means where that reaction is being applied or felt. Okay. To find any reaction, we need to see the moment about one of the points. You can either pick A or B, and you can say I want to find the moment about that point. So let's say moment about A. Moment at A. Okay, the sum of all the moments should be 0. Okay, so this is what we'll do. So to calculate moment about A, we calculate, so we pin this, we pin this here, and then see what the moment is from all these rotations. When you apply RB, RB tends to rotate this beam. Well, can't really see green on black. Okay. So RB tends to, well, can't see that color either. Let me pick a lighter color. So RB, alright, RB tries to turn the beam in that direction. When it is pinned here at A and you apply RB, it rotates the beam in that direction. Okay, and how much is that moment? It is RB, right, times the distance, which is 4 plus 5 is 9, from the point of application to the point where it is pinned. So I'll say pinned. I'm gonna put this because not in the problem in this question the beam is not pinned, but while calculating the moments we have to assume it is pinned here. That way we get the moments. Okay, all right, that's why I've put it under quotes. It's not really pinned. A pinned joint is something different. Anyway, so RB times 9, and then minus the another load is this uniformly distributed load here, right? And how much is that? It is 18 times 4, that is the force, times the distance. Now the distance is, like we have said before, we always assume the uniformly distributed load is acting at its center here. Okay, so the 72 Newton is acting at the center, so that means 2 meters from here, right? So 2 meters from here. So I'm going to write 2. And negative, this is negative because this weight, when it acts, it pushes it down and tries to rotate this beam in this direction. So we're calling this direction as positive and this direction as negative. Okay, so I'm going to erase this. Okay, so this is equal to 0. Sum of all the moments is equal to 0. From this we get RB as what? 16 Newton. So I'm going to put 16 here. Okay, similarly, sorry, RB is 16. I should put it here. Okay, now RA, there is another, so we can do the same thing now, pinning it at B and then calculating the moments. We can do that way, or there's a simple way, which is in this beam is standing still, right? It is not falling down. So all the forces and moment, all the forces should be equal to 0. The sum of all the forces should be equal to 0. Okay, what do we do? So let's do one thing. So all the forces up should be equal to all the forces that are acting down. What is up? This RA is up plus RB is up, right? There's nothing else. On the down, it is only this 72. How did we get 72? 18 Newton per meter times 4 meters is 72. Okay, so RA plus 16 equals 72. So RA is equal to 56 Newton. So this is 56. Okay, so from this information we will go ahead and create the shear force diagram first. Okay, I'm going to erase this part here. I'm going to erase all of this. So the shear force diagram is quite simple. So this is what we'll do. All right. So we have 16 here. So the force is up. So we go down. And like I said, imagine you're standing here and you're marching backwards. All you see is 16. Here, 16. When you're here, you still see only this force. Same way all the way up to here. So you go to 16 up to here. Okay, so this is 16. Now the 70, so now you have this 18 times 4. 18 times 4 is 72. So we need to go 72 up. But if it is a point force like this, if it's a point force, then your shear force is constant like this. But as soon as you have a uniformly distributed load, the shear force is not horizontal, but it becomes linearly increasing. So this will increase linearly up to here. Okay, and this will be from 16. So this is 16. This is 16, and from here to here should be 72. So from here it's going to be 56. Okay, so here it's going to be 56, which is again the reaction force here. So even if you were to draw this shear force from this side, it would still be the same. Okay, we would start off with 56. See, RA we calculated as 56, right? So we'd start off with 56 and then decrease this way until we got to 16, right? And then move until we got to point B. Okay, now somewhere here this is crossing the x-axis line. This is intersecting the x-axis line, and we need to find where. The significance of this point is that at this point the forces are 0. Forces are 0. The sum of all the forces, the shear force is 0. The beam sees no load at this point. Okay, and we need to find where that point is. All right, let's go about doing that. Let us say this point here is some x units from here. Okay, so remember so this is 4, and from here to here this is 5, right? So somewhere, so this is x. Obviously this distance would be what, 4 minus x, right? It does, and this x, you can choose this x in any way. You can choose this x from here too, doesn't matter. Okay, so it always works out the same way. All right, now we have x. We know that the sum of the forces is 0 there. Okay, sum of the forces is 0. So let's go about adding all those forces. Okay, first we have 16. Right? We have this force 16. We'll take that as positive, minus this uniformly distributed load, right? These are the only two forces here, right? Sorry, only three forces here. Right. So let's go about this. I need to explain one more point before we get to this. Let's do the same thing as we were doing, starting from here, going backwards. Okay, so we have gone all the way back up to here. Okay, now when you're standing here, let's see all the forces that you see from here. So the 16 that you see, plus there is a uniformly distributed load from all the way from here to here, right? So we need to know the weight of this part, how much that weight is. Okay, and how do we find that weight? We find that weight by taking the 18 Newton per meter, right? So that means 18 Newton per meter is the distribution, right? For every meter we have 18 newtons. So if we multiply this by this length, then we get the weight of that portion. Okay, so and how much is that distance? It is 4 minus x. Okay, and we're saying the force here is 0. Okay, so to recap, to find this distance x, to find where this point is, we say, okay, let this distance be x away from this end, right? And then we do the same thing as we were doing for calculating the shear force diagram, right? So we stand here and we're moving backwards. So when we're moving backwards, we keep seeing only the 16 Newton force, so that we have here. When we come here, we need to add this force also. That force is what? The distribution, Newton per meter, times the distance. So this entire distance is 4, which is given in the problem. And we have said this part is x. Right? So the rest of it would be 4 minus x. Okay, so we have multiplied the distance, and then we get from this, when you reduce all of this, what do you get? 16 plus 72 minus x is equal to 0. Okay, no, I'm missing something. 16 minus 18x. 16 minus 72, right? Oh, sorry, this should be negative, because this 16 is acting up and this weight is acting down. Sorry. Right. So 16 minus, let me just erase that and rewrite it. Okay. So 16 minus 72 plus 18x is 0. So you get x is equal to, let me see, so 56 over 18. So that's let me see, it's 3.11 meters. So this x is equal to, this is 3.11 meters. And so I'm going to erase this here and say this is 3.11, so this will be 0.89, because both of them should add up to 4. Okay, now coming to the bending moment. Okay, so for bending moment, let us draw a line. The bending moment at this point is 0, because we have the force 16 multiplied by distance 0. We're standing again. We're standing here, so x is 0, right? So it is 0. And the bending moment will increase up to this point, up to point C. Okay, how much would that be? Right, what is the moment at C? The moment at C is the 16 times this distance. 16 times, which is, this is 5 meters. So 16 times 5 is 80. So this will be 80, which is 16 times 5. Okay. And this is connected by a straight line. Why? Because when the force is horizontal, then the moment is continuously increasing in a straight line. Now when the shear force is increasing in a straight line, then the moment becomes parabolic. Okay? So the next point we need to find is the moment at, let's call this point D. Moment at D. Okay, so to find the moment at D, what we need to do is same thing. We'll say each distance times each force times the distance there. So first see 16 times this distance, so that will be 5 plus 0.89, correct? So 16 times 5 plus 0.89. Okay, and then we have, so this force is trying to go that way, so we'll keep that positive. And then there is a moment due to this distributed load, which is downward, so this will try to rotate this beam this way, so that will be negative. So here, let's see, so what is the weight of that portion? It is 18 Newton per meter times the distance, which is 0.89. This is the weight, right? This is the force. Once you multiply this distributed load times that length, you get the force multiplied by this distance. Multiplied by which distance? Now we have discussed before that for a UDL, the distance, we're assuming that this distributed load, let me erase it, make it a little bit neater. Okay, so this distributed load is acting at the center of that load, right? So this is 0.89, this distance is 0.89. So the center of this will be half of 0.89. So we only want, so we say that this entire load is acting at the center. So what is this portion? This is 0.89 divided by 2. Okay, so the distance is 0.89 divided by 2. So this is the entire moment at point D. That's the moment at point D, and when you do the calculation you get 87.11. Okay, so we get 87 at point D, 87.11, and this is a parabola. Now from here you can simply connect it back to here, because when you calculate the moment the same way at this point you will get 0, right? So with the parabola, so this is a parabola, this is also a parabola, and this is a straight line. Okay, so 0, 80, 87.11, and back to 0. So the only thing to remember here is where we need to find this point in the shear force bending moment diagram. We got something like this. So we need to find that point. Okay, we find that point here because in the shear force diagram this is 0. So so the force is equal to 0. So we again do the same thing. Start from here. Whatever loads you see, this is 16. We say 16. Move back, move back, move back, move back, move back. Come here, right? So here we see that the forces here is minus whatever the force is due to this uniformly distributed load from here to here. Okay, and this is point number 1 that you need to remember. Okay, so in our case we got what did we do? We said that way that 18 is the density or the linear density, right, times that distance was 4 minus x, right? That's what we said. So this distance is 4 minus x. As an exercise, what I want you to do is take this as x. Take this as x and do the problem. We know up to here it is 5, okay, and this entire thing is 9. Okay, so solve the problem using this setup and see what you get. Okay, you should get the same answer. Second point to remember is when you're calculating moment, let's say you want to calculate moment about some point A, okay, and then you have a uniformly distributed load, okay, and this is say 20 Newton per meter, and this is 2 meters, so it becomes 40 Newton. So this 40 Newton, you have to assume that this 40 Newton, right, 20 times 2 is 40. This 40 Newton is acting at the center here of this uniformly distributed load, is acting at the center. So the distance from here would be, let's say this distance was 3. So while calculating the moment, you say from here to go to the center of that distributed load, right? So this would be 3 plus this is 1, right? So 4. So when you're calculating the moment, you use this 40 Newton times 4. So 40 Newton acting at a distance of 4. So these are the 2 points you need to remember while solving this question. Also, as an exercise, what I would want you to do is we simply connected this back to this point because there is nothing else going on between here and here. There's nothing else going on there, so we simply connected this back to 0. But as an exercise, calculate the moments at point A using all these loads, using the 16 times 9, and then 18 times 4 is the load, 72 times 2, right? So this should cancel out to 0.